What we're going to focus on in this segment is how the structure of the leaving group that breaks away during the course of a nucleophilic substitution reaction will impact the rate of that reaction. In other words, can we carefully select what leaving groups we use in our starting materials in order to make nucleophilic substitution reactions go more effectively? The way I like to kind of look at this is asking ourselves, can we sort of hack nucleophilic substitution reactions to make them do what we want and to make them do it faster? Because certainly nobody likes to sit in the lab waiting for a reaction to take place any longer than you absolutely need to. So what we're going to be looking at is our general nucleophilic substitution reaction, which we see here on the slide. And remember that regardless of whether you're looking at an SN1 or SN2 reaction mechanism, that the rate limiting step is going to involve the leaving group breaking away. So regardless of whether it's SN1 or SN2, and we went through those mechanisms at length in earlier segments, so make sure and go back and review those if you're asking what in the world I'm talking about right now. The leaving group breaks away during the rate limiting step of SN1 and SN2. And so when we're thinking about so-called hacking this reaction or the impact that the structure of that leaving group is going to have on the reaction, we can make the reaction go faster if we use a leaving group that will be more stable on the product side here. So the more stable the leaving group, the better the reaction is going to go and the easier you're going to get out of lab. So we want to take a look at factors that will stabilize that leaving group product, because the more stable this leaving group product is, the better that reaction is going to go. In other words, the faster that reaction is going to work out for you. So let's take a look at factors that will stabilize leaving groups. And this applies both toward SN1 and SN2 reaction mechanisms because of the fact that both mechanisms involve the leaving group leaving at the rate limiting step. So we're asking here, in other words, what constitutes a good leaving group? A leaving group that is willing to break away readily to get your reaction underway. So what constitutes, or what factors create a so-called good leaving group? So we're looking at what's going to create a good leaving group. And in order to evaluate that, we look at that reaction of our electrophile, that's our carbon that's directly bonded to our leaving group, with our nucleophile and the product that that yields. And it's very commonly the case that our nucleophile is an anion. So for this particular generic scenario, I'm going to put in nucleophile, it's negative. My ends of the line here are just going off to whatever atoms we want. We're going to replace the leaving group with the nucleophile once the leaving group breaks away to maintain the formal charge here. I'm going to put that as LV ... with a negative formal charge. All right, so in other words, we're asking to evaluate what constitutes a good leaving group. What we need to look at is what's going to stabilize the product side of the reaction. So in the product side of the reaction, the thing that we can vary to create a specific targeted product here, we usually have a specific nucleophile in mind that we want to form a bond to that carbon atom. So we can't really alter that, but we can alter what we use as our leaving group here, since that's what's going to break away during the course of the reaction and essentially be trashed at the end. So if we can create a situation where this leaving group product is more stable, that's going to promote the nucleophilic substitution reaction in taking place. So we have to ask ourselves here, what factors will stabilize the structure of that leaving group? You'll notice that leaving group is oftentimes an anion, and so we can think back to factors we know of that stabilize bases or conjugate bases as factors that we can also consider here for stabilizing our product. So since we established that what constitutes a good leaving group is a leaving group that will be really stable once it's left, then the next question on our mind is what increases the stability of that leaving group product, because we want that product to be as stable as possible if we want the reaction to work as well as possible. All right, so factors that are going to increase the stability of that leaving group, we're going to look like really similar here to our conjugate bases or bases, what will stabilize those. So what stabilizes a base or a conjugate base to make that less reactive, more favorable, is going to be, first off, either having no formal charge is the best case scenario, because if there's no formal charge, that's generally going to be a more stable molecule than having a formal charge, or if there is a formal charge on the leaving group, then it's best to have that formal charge on the most electronegative atom. So no formal charge is the best case scenario, or if we can't do that, having the formal charge on a more electronegative atom is more favorable. So that's that. Second item on the list here, and again, this list is looking a lot like deja vu of factors that stabilize conjugate bases. Second is having a larger atomic radius, because the larger atomic radius gives those excess electrons of the anion more room to roam. And this typically applies most strongly toward atoms that are in the same column of the periodic table. So atoms that are in the same group of the periodic table, we're typically going to look at the larger atomic radius as being the most important factor. So if you're comparing, say, an oxygen and a sulfur, the larger atomic radius of the sulfur is going to help stabilize the sulfur anion relative to an oxygen anion. Hence, sulfur is going to be a better leaving group than oxygen. All right, going onward on our list, resonance. If we can share the negative formal charge over multiple atoms, that's going to improve its stability. So resonance sharing of the formal charge is going to improve the stability of that formal charge. Go onward to number 4, which is generally going to be the least important of these 4 factors, and that is going to be induction. And specifically, induction remembers that bond polarization effect through multiple bonds, and by induction, groups can either donate electrons, such as we would describe alkyl groups as donating electrons, or they can withdraw electrons, which is typically the case for atoms that are more electronegative than carbon. We would typically consider to be electron withdrawing. So oxygen, nitrogen, sulfur, halogens, etc. withdraw electrons by induction. So if we have a leaving group that has a negative formal charge, do we want a group bonded to there that is electron donating or electron withdrawing? We would want a group that is electron withdrawing, because the leaving group already has more electron density than it needs. It wants to get rid of some of that, and the way it gets rid of it is by polarizing the bonds, using electron withdrawing groups to draw some of that electron density away from the negatively charged leaving group. So induction using electron withdrawing groups, because electron withdrawing groups stabilize the negative formal charge. So electron withdrawing groups, just like I said a moment ago, are going to be generally electronegative atoms. Some examples of those are going to be X, meaning a halogen atom, nitrogen, sulfur, oxygen, etc. So if we have some of those in the vicinity, a couple of bonds away, those are going to help to polarize bonds, drawing electron density away from the leaving group and thereby stabilizing by helping to spread out to some extent that formal charge. But induction, I would put definitely dead last on this list here. Resonance, typically more important, because that you can show that the formal charge can be fully shared over multiple atoms by drawing resonance structures. Induction is just the polarization of bonds, so it's a more gentle, less strong effect. And certainly above both of those is going to be either having no formal charge or having the formal charge able to be on the more electronegative atom is typically going to be more important, or the business of the atomic radius. So let's take a look at a couple of example problems here to illustrate hacking reactions to have better leaving groups so that we can get a better, faster outcome out of the reaction. So what we're going to do here in this example problem is we're going to rank the 4 molecules that I'm going to show here in terms of what you would expect to react fastest to slowest. All right, so taking a look at this example problem, we're going to rank the 4 compounds below in order from the fastest to the slowest in an SN1 reaction with methanol. So the approach that we have to take in order to do this is we look at these structures. The difference between them all is just what leaving group they have in each case. So we need to be comparing a chlorine leaving group, hydroxy leaving group, amine leaving group, bromo leaving group to determine which is going to react fastest. The one that reacts the fastest will be the one that yields the most stable leaving group. So we need to look at the leaving groups that will be present in each case. So our leaving group for the top scenario is going to be the chlorine atom breaks away, giving us chloride. So you have Cl minus. Our hydroxy group can break away, giving us hydroxide anion, OH minus. Our NH2 group can break away. And by the way, that NH2 would have a lone pair to start with. And so when we break that carbon-nitrogen bond, that nitrogen would end up with 2 sets of lone pairs, 2 sets of lone pairs, and 2 covalent bonds, means it has a -1 formal charge. And then our bromine would break away here as well to give bromide anion. So we have to rank these according to their stability, where whichever one of these is the most stable product will lead to the most favorable nucleophilic substitution reaction using that leaving group. So looking at these and thinking about those factors that stabilize, the first thing that we need to consider are the issues of electronegativity and atomic radius. As we move from left to right in the periodic table, we're increasing electronegativity. And so based on electronegativity arguments, we're going to eliminate our nitrogen and oxygen because our chlorine atom and our bromide are both further to the right in the periodic table. So we've narrowed it down to those 2 as being the 2 candidates for most stable. And then once we're in the same column of the periodic table, we judge based on atomic radius. So chlorine and bromine in the same column of the periodic table, but bromine has the larger atomic radius, and so therefore bromine is going to be the winner. So chlorine, not the winner. Bromine is the winner. And so we're asked to rank all 4 from best to worst. So best case scenario is going to be the bromine leaving group. Second best case scenario is the chlorine, and then comparing the oxygen anion to nitrogen. Oxygen is more electronegative than nitrogen, and so oxygen is going to be better able to handle that negative formal charge, so we're going to put that number 3, and the nitrogen is the big loser here. So we'll go forward now and do another example problem of looking at leaving groups and evaluating what's going to be able to act as the best leaving group within a molecule. So now we're going to go about comparing these 3 molecules in terms of identifying which one has the best leaving group and hence would react best in a nucleophilic substitution reaction. So first things first, we need to identify what in the world is the leaving group in each of these cases. They look a little bit different in some cases than the molecules we've studied before. So remember that the leaving group is going to be the heteroatom that is bonded to an sp3 carbon. And so as we look at this molecule down at the bottom, our leaving group is going to be our group here that I've boxed in pink and red. And our electrophilic carbon atom, by the way, would be that carbon atom right here that's directly bonded to that. So during the reaction, we'd be breaking that carbon-oxygen bond. Our oxygen would be acting as the leaving group. And so we can write the structure of that leaving group as our strategy for solving this reaction. That our leaving group structure would be like so. If we come up to the middle scenario there, our hydroxy group, OH, is going to be the leaving group. And we can show that breaking away, much like we did at the bottom case where we have the carbon-oxygen bond break. And remember that carbon that's bonded to the oxygen is the one that's going to be our electrophile. So we'll go ahead and write the product of that reaction step, which would be a hydroxide anion is what results there as our leaving group that's broken away. And then we come up to the top scenario here, which represents a case where OH group has gained an extra proton. For example, if you put a alcohol solution into sulfuric acid, the sulfuric acid will protonate the alcohol group to give OH2. So our leaving group here, same sort of game that we were playing with the other ones, is going to be the electronegative atom that's directly bonded to a carbon. So we're still going to be breaking away that oxygen atom here. And we can show that breaking away like so. The electrons go onto the oxygen. And here, when we do that step, the leaving group product is going to be H2O, water, in other words. So we go ahead and do that like so. And now, in order to assess which of these molecules that we started with has the best leaving group, we need to compare the stabilities of the three products that would result, the three leaving groups that have broken away here. So looking at these and going back to that list of criteria for evaluating the ability of a leaving group to leave, the first thing on the list was having the negative formal charge on the most electronegative atom, or even better, having no formal charge at all. And so for that reason, our winner here is definitely going to be water. Of these three leaving groups, water is the best because it has no formal charges. So we have no formal charges to fuss with, and that's going to create a very stable leaving group. We ask for the best leaving group in this question. Let's just go ahead and be a little bit of an overachiever here and now go in and rank the other two to come up with what is the worst leaving group. So looking at these other two structures and kind of thinking about our list of criteria for determining whether a leaving group is good or bad, both of these have a negative charge on the oxygen. The hydroxy group in the middle has no resonance, but if we look down at the structure at the bottom, we can indeed draw a second resonance structure for this to show that we can move that negative charge and share it over multiple oxygen atoms. So we can take the lone pair of electrons and bring that over to make a covalent double bond, move the pi bond up onto the oxygen like so, and we can write out what will result from that process right here. So I have three sets of lone pair electrons on that oxygen up top now. And now what we've shown is that we've shared that negative charge over two oxygen atoms. Sharing is caring. Sharing is going to create a more stable product than the situation above with the hydroxide anion where the electrons can't be fully shared by resonance. So we're going to rank this as second best. And it's second best due to the effect of resonance. And our big loser here is going to be the hydroxide anion. Is going to come in last place. It is the least stable, and therefore if we're thinking about which of these molecules is going to react best in a nucleophilic substitution reaction, the one you want to pick is going to be this one at the top. The one you want to steer clear of is going to be the one with the hydroxy group on it, the alcohol, because that's not going to yield a stable leaving group. So with that, what we've done here in this segment is introduced how leaving groups can impact the ability of nucleophilic substitution reactions to take place effectively. And so as you're thinking about setting up nucleophilic substitution reactions, one of the things to keep in mind is you want to set them up in a way that will allow you to create the most stable leaving group, because that's going to lead to the most favorable reaction.